The next part of this chapter is talking about here the effective root mean square value, and then there's something called complex and complex power and power factor and so on. So what is the root mean square value for a DC, for a AC current? Okay, this is the DC current, the value of the DC current that produces the same power. Simple like this. So if you have a DC source like this, okay, and you have AC, then the effective or root mean square value is the DC value that will give the same power of the AC. And it is described by this value here, by this equation. It is 1 over T, 1 over the period, time the integration over the period from 0 to T of the power P of T dt. So here it is actually, we replace P of T by I square R, okay, I square times the resistance R, and you can see here, this is what we call it here, I effective or I root mean square value. Then if you just remove this R from here and R from here, then I effective is the square root of this part here without R. So it is 1 over T square root of our integration from 0 to T I square dt. So this is the root mean square value expression. Of course, if it is current or voltage, it is the expression is the same. There's no difference. Okay, and usually it is maximum value divided by square root of 2. So if you have, for example, the current equal 10 cosine whatever omega t, then in this case the effective value or the root mean square value is this 10 maximum divided by square root of 2. Square root of 2. It's very easy to explain it here, because it is actually here if I, for example, here is I cosine, is I m cosine. So actually when you square it would be I square times cosine square. And to integrate cosine square, it is hard it is not easy to integrate cosine square as it is. You have to convert it to its cosine value or cosine equivalent, which is 1/2 plus cosine 2 omega t. But cosine square 2 omega t, it is not easy to, you cannot do it right now like this. You have to convert it to cosine 2 omega t like this with this formula. And when you integrate this part here, you will find that the integration here, the integration of this part here is actually t. You can prove that. You can prove that this integration here equal t. So t will cancel with this t. So you end up with what? You have this 1/2 here. So this 1/2 is like this. So actually it's t over 2. It's t over 2. So t will cancel with 2. You end up with im squared divided by 2. So when you take them outside, then it will be im divided by square root of 2. Okay. So this is the root mean square value. It is simply the maximum divided by square root of 2. So if we have example like this and we need to find the root mean square value, then we apply the formula I root mean square value equal 1 over t square root of 1 over t integration of I square dt. Okay, so equal to, if you have a periodic function like this, it is defined different for each period. It has two definitions from 0 to t to 2. It has it has this function here, and from 2 to 4 it is different. So you need to use the two periods. So to integrate over the complete period from 0 to 4, you have to divide it into two parts, from 0 to 2 and from 2 to t. So it will be 1 over t, 1 over 4, integration from 0 to t. From 0 to t, it is 5t. So it will be 5t square dt. And from 2 to 4, the value is negative 10. So it will be negative 10 square. Negative 10 square. As in the integration of 5t square, 5t square is what? Is 25t square. 25t square the integration will be 25t cubed divided by 3. So this is the integration from 0 to t. And you substitute by t equal 2 and then t equal 0. Then you can calculate this one will be 200 over 3. Because in this case, when t equal 2 will be t cube will be 8. 8 times 25 is 200. 200 divided by 3. When t equals 0, it's just 0. Here, negative 10 square is 100. 100 from 2 to 4 is just 100 times the difference here, which is 2. 100 times 2 is 20. It's 200. Okay, so you add, you simplify this, and you can find the root mean square value of the current. If you want to calculate the average power absorbed by resistor 2 ohm, so you can use this formula here. I root mean square value, which is this one here, 8.165 time square time R. So that's it. This is, you can use this formula to calculate the power absorbed in this resistor. If this is a current, okay, so this will be the power in the resistor, the 2 ohm resistor. I root mean square value, this one here square, time R, which is 2. That's it. What is a power factor? So power factor, okay, this actually, when you have more power factor, the higher the power factor, this means that you higher absorbed power, which is good. So it is actually related to what here is this part here, this part. This is what we call it, power factor. It's a power, the average power is 1/2 Vm Im cosine theta V minus theta I. It is the same like this one here. You can also represent it in root mean square value. They are basically the same. But this part is what we call it cosine, the difference between the phases theta V and theta I. This is what we call it a power factor. So if it is 0, if the difference is 0, so cosine 0 is 1. So this is a maximum. And if it is 90 or negative 90, then cosine 90 or negative 90 is 0. This is the lowest power factor. So the power factor is ranging from 0 to 1. 0 to 1. Okay. It will be 0 for what? It will be 1 for what? For resistive element. If you have resistor. If you have resistor, there is no phase shift. If you have resistor, you don't have any phase shift. Okay, so in this case, the power factor is 1. Okay, this is purely resistive element. But if you have reactive element, if you have only capacitor or only inductor, the phase shift is 90 or negative 90, then the difference between the phases is 90 or negative 90. Cosine of this is 0. So the power factor is 0. We have this long problem. It looks like it is long, but it is nothing here. We have some series loads. We have the current. This is the current. Okay, and this is the voltage. Okay, we need to find the power factor. So what's the power factor? Is cosine the difference in phase. It's very simple. Cosine the difference in phase. The voltage here is negative 20. The current is 10. What is the difference in phase? It is negative 20 minus 10 will be negative 30. So cosine negative 30. That's it. This is the power factor. So the power factor is the cosine, the difference in phase between the voltage and current. Theta V is negative 20. Theta I is 10. So it will be negative 20 minus negative 10 cosine. Cosine negative 30 will be this number here. So this is the power factor. Okay. So this is the first part. We need to find the average power of the load. The average power of the load is 1/2 Vm time Im cosine the difference in phase. So you can use this one or you can use this one. Doesn't matter here. So here they use a power factor, the root mean square value, but you can use a formula that we have before. 1/2 time what? Time the maximum voltage here is 12, 120. Okay. Time what? Time the maximum current here is 4. Cosine the difference here, which is a power factor actually. Cosine the difference, which is power factor. So time 0.866. That's it. And you will get the same answer. Of course, it is the same answer because this one compared to this one is the same, because the square root of 2 times square root of 2 is 2. Okay. So this is the average power. And then find the elements values that form the series connection. This is actually maybe not related to the power, but if you want to find what kind of element is this, what kind of element, I don't know. So what kind of element, you can just say, okay, I want to find Z. So what you need to find here is Z. Z equal what? Z equal V divided by I. That's it. Okay, so it will be have a real value and imaginary value. That's it. V is given. V here it is 120 cosine, and this is I 4 cosine. Okay, so you can just find it like this. V is what here is 120, and angle negative 20, and I is 4, and angle 10. So it will be 120 divided by 4, that's 30. And angle what? Here the angle is negative 20 minus 10 will be negative 30. Okay. Then what you need to do is just convert this to real and imaginary. So it will be 30 cosine negative 30 plus j 30 cosine or sine negative 30. And when you do that, you will find this is a real and imaginary. It will be like this. Since you see here, as we did here. Okay, so we convert it back. So this is the real, this is the imaginary. Okay, so now the real part is the resistive here, or the resistance is 25.98, and the imaginary is negative 15. Negative 15 indicates that this one is capacitive load, because we know that the impedance of the capacitance is 1 over j omega c. 1 over j is negative j. If it is inductive, then it's supposed to be j omega l, and j is just positive, of course. So here, since the imaginary part is negative, we know that it is actually capacitive part. Okay, this is, of course, this is just this is one of the possibilities, but there is another possibility that you have, for example, inductor and capacitors in series, but the capacitor is more than the inductor. The impedance of the capacitor is more than the inductor, so the negative is more than the positive. Then the total will be negative. The total will be capacitor. And here you can just, if you want to calculate the capacitor, what kind of capacitor, we know that XC is 1 over omega C. 1 over, this is 1 over J omega C, of course. This one, 15, will be 1 over omega C. 15 will be 1 over omega C. Omega is 100 pi. This is omega. This is omega. Omega is 100 pi. And C, you can calculate C from this number, from this equation.